Hello. We're going to do a little bit more complicated example of an application of a motion, a circular motion. Um, so a car is going round a bend, and this part, you can think of this part as a part of a bigger circle. Which radius is 50 meters, but the road is not really flat, but the road is one end is higher than the other end, and this angle is called angle of banking, and that's taken to be 30 degrees. For numerical calculation we'll do over here. First we'll do it calculation symbols, and then we'll do numerical calculation. And its coefficient of static friction between the road and the tires is also given to us. Okay. All right. So we will assume that we have a speed is constant while going through the bend. Of course, when you go through a bend, over here you slow down, and then you speed up here. But we're going to say over here you have a constant speed. So just assume constant speed here. Well, if you have a constant speed and you're going in a circular arc, you know the acceleration will be in that direction. So that will be the acceleration. So we need to identify forces whose net effect is the acceleration in that direction. So let's look at the forces that's going to be. So if you, this is a pretty complicated diagram here, and if you say what's the force? Force will be a gravity away perpendicular to this flat part of the road, not the wedge kind of shape. So gravity will be like this, coming down. The normal force, so if you look at the road shape like that, road is shaped like that at any point, and acceleration is in that direction, and so the normal force will be in that direction. Static friction force will be in that direction, and gravity will be straight down, perpendicular to this. Gravity will be straight down. So what we will do is try to draw this diagram so that it's easier to work with. So let's see what the diagram looks like. Well, we could draw this like a horizontal line. So let's look at, so this is a cross section of the road, and this side is higher and this side is lower, and the circle is like that. So this is where the center of the circle is. So acceleration is in that direction, and that's centripetal acceleration, and there's no other acceleration. So the net force has to equal to that. So let's see. If away from that, perpendicular to that is back. So we're looking from the back. So looking from the back of the car. So this is the view from the back of the car. All right. So front and back, we're not interested in that because we just want to know the speed which is going, and that speed can be obtained if I know the acceleration. So let's see. Weight is straight down. It's the flat side, bottom of the road, and this is mg. Of course, mg is not going to participate directly in this, except it's going to participate through the normal force. So normal force is that way, which is 90 degrees here. Let's call this theta. And so we're going to do Fn is magnitude, and static friction will be down below, because if it wasn't the case, I couldn't have this acceleration. so Fs. And you can see that acceleration is kind of the net of these two is in the direction of acceleration. We can use we can use the axis here, regular axis. So this is can be y-axis. Let's call this y-axis, and I'm going to just draw x in that direction. So I'll have some positive AC. I like to do that. If I know which way the acceleration will be, I'll just point x-axis, positive axis toward that. So this is theta, then this will be theta. So we are going to get equations in the x. So we're trying to write F equals to ma, F net equals to ma. So we're going to write this x and y. Along the x, I'm going to get nothing from the weight, and and Fs we want is a maximum, and so this is equal to mu s Fn. So I can just use this right away. So this will be mu s Fn times cosine theta. So that's one of the force component, and then if this is theta, this 90 minus theta, so this will be theta. This angle is also theta. So this along the y-axis, the Fn gonna give me positive in the x, but it's going to be sine theta. Fn sine theta equals now m of the car, v square of the car, and the radius of the circle is going in. So that's one equation. So this is my x equation. The y equation will be have Fn. It's not along the y. It's adjacent. So it's going to be Fn cosine theta. And then this guy will also have a component, but it's negative, mu s Fn sine theta, and then weight will be negative minus mg, but there's no acceleration along this direction, so I'm going to get equal to 0. So these are two equations. We can try to solve it. Solving 2 for Fn gives me Fn equals to mg over cosine theta minus mu s sine theta. So I got that for Fn, and all of these are known. If the mass of the car is known, it's not given over there, but if it was given, then other things are given. So this is say number 3. Using Fn in 1, now I use this in there, then I can solve for v. So we have in here Fn is common, so I get a sine theta plus mu s cosine theta times Fn equals mv squared over r, and I just put in there. Then I get a sine theta plus mu s cosine theta times mg over cosine theta minus mu s sine theta, and that's equal to mv squared over r. So now I do have a cancellation of m on both sides, and so this multiplied by gr on this side gives me v squared. V squared is g times r, and then I have a combination of all of these guys, g times r times sine theta plus mu s cosine theta over cosine theta minus mu s sine theta. So if I was looking for, this is the maximum speed because I'm using the maximum amount of friction. So if I can get the v, that's going to be square root of all of this stuff. Gr sine theta plus mu s cosine theta over cosine theta minus mu s sine theta. Now put in numerical values. So what will I get? I get, so G is 10. Let's try 9.81. Okay, because I'm going to put in the calculator. And R is 50. And sine 30 degrees is 0.5 times cosine 30 degrees divided by cosine 30 degrees minus 0.5 sine 30 degrees. Okay, so if I were to put this in a calculator, I should get some value. And let me try some calculator here. Okay, so I used my calculator and I got 27.3 meter per second. You may want to do your own calculation. We didn't find what the normal force was, but for that I needed the mass of the car. But you can see here, if I just want to look into speed, mass of the car cancels out. That means this speed can be posted for all cars. So the maximum speed would not be different for different cars because this mass just cancels out. All right.